Okay, so we're done our graphing assignment. You may have noticed I'm not here today, and that's just it's been a very difficult week at home, and I'm not feeling good. My wife's not feeling good. We haven't been getting enough sleep, so I'm hoping that this helps kind of recharge a little bit. I know you have no scheduled class tomorrow. I'm away anyways, as I'm going to a wedding this weekend. So I'm going to try to record this lesson. It's not too bad. It's something that we've kind of done already before that we'll talk about, but we're going to talk about solving rational equations. And so to start, we're going to warm up and refresh what we've just been talking about, and we're going to graph this function here. So I'm going to take a moment here, write some of the characteristics down, and we'll talk about what they look like on the graph. Okay, so I've written down we have an x-intercept coming from where the top is 0 at -1. For this graph f of x, I maybe should have color coded the two graphs. I'm just realizing I can save it. We're good. And because I'm sleep deprived, I accidentally put the y-intercept at -1, but no, it should be the x-intercept at -1. So this crossed out point is incorrect. Our y-intercept is at 0, 1/2, because if you sub in x equals 0, you get 1/2. So I put that point on at 1/2, and then vertical asymptote at x equals -2, where the bottom equals 0. We have a vertical asymptote at -2, and our horizontal asymptote, the coefficients are the same, so it's not at 0. 1x over 1x, 1/1, y is equal to 1, and I put that asymptote on here as well. And so we have 2 points here. That's going to be pretty easy to understand this shape here. And then we can find at least 1 point up here. And we'll do that for now. So I found, well, if we go left of this asymptote, we can maybe plug in -3, and we get our y equals 2, subbing -3 in there. And so with that point, following the asymptotes, we can get this shape here. With these 2 points, we can get this shape here, following both of those asymptotes, and that's our function f of x. Now, this question also asks us to graph the function g of x on the same set of axes. So we can do that in the y equals mx plus b form, where we have a y-intercept of -1 and a slope of -1. And let's see what that looks like. And so I've done this one in black. And so a y-intercept of -1, we go through that point I crossed out earlier. Again, not a point on the green function. But turns out it is a point on the black function. And it has a slope of -1, so going down and to the right. And so this is our line here. And we can see it crosses that rational function 2 separate times. Once at -1, 0, and once at -3, +2. So those 2 points of intersection, we're going to see where they may come up here in just a moment. And we're going to try to solve this type of equation algebraically. And so this actually does look somewhat similar to what we had talked about when we were trying to figure out where are we crossing asymptotes. Where are we crossing horizontal or oblique asymptotes. We solved equations that looked kind of like this. Now we're going to talk about that process a little more formally here today. And that really is what we're talking about when we're solving a rational equation. An equation that has a rational expression inside of it. And so we had those 2 points of intersection that we just circled. Now when we try to solve this equation, when we were doing equations like this previously, well, we can multiply out our denominator. So here it's going to cancel out. We're going to multiply by x plus 2 on the right side. And we can expand those brackets out. So -x times x, we get -x squared, -x times 2, -2x, -1x times x, we get -x, -1 times 2, you get -2. And so from here, we can move everything over to the left. So I get a positive x squared, x plus 2x plus 1x, I get 4x. 1 plus 2, I get 3, which I can factor. And then finally, I can solve x equals -3 or x equals -1. And now, if we compare that back to our 2 points of intersection, well, here, that was x equals -3. This was x equals -1. The points of intersection, we could find y values too, but it has the same two x values, -3 and -1, as we just got algebraically. So our general strategy when we're doing these rational functions, which we didn't do all of these steps here, but we would want to make note of the restrictions to make sure that our final answer doesn't contain, oh, there's that word again, doesn't contain any extraneous solutions. So that word we used in our log unit as well. An extraneous solution is something that makes sense algebraically at the end of our solving, but didn't make sense back in the beginning. So one example here would be if we got an answer of -2 somewhere here, that wouldn't make sense up here because that would have been a vertical asymptote in this function f of x. I wouldn't be able to have any x values at x equals -2, even if it ultimately solved there. So we want to make note of any restrictions in the beginning to make sure we remember x can't equal -2. Same as our log functions, we made note of those restrictions. We want to do that first. Probably same as the logs. I'll tell you that you need to state those, but yeah, you do want to state those in the beginning. And then check, are any of these extraneous? Oh no, they're okay. Multiply out our denominators like we did. We multiplied out x plus 2, and then we solved. We just had a polynomial equation. Here was a quadratic equation. We know how to solve those things. So I'm going to flip over to the second page here. And one-handed fold. We're going to look at a few more here. So this second one, let's see what we can do for example 1a. So in this equation, I have an x minus 4 here. Well, I can multiply that out by multiplying both sides by x minus 4, and those two things will cancel. Can I do this without? So I'll save that for a moment. And then this one I can multiply by x plus 2 on both sides, and that's going to help cancel that out on the right side. And so we're going to get that x plus 2 that didn't quite cancel because this one canceled on the right, and this x minus 4, canceled on the left. And we just get these. Oh, I guess I should. Sorry, I keep bumping the sheet. Should cancel that, should cancel that. And so we would just get left with x plus 2 times x plus 3, x minus 1 times x minus 4. We have quadratics on both sides, so expand out your brackets. Collect all your like terms on one side. So our x squared, if you subtract that, it's going to cancel out with that x squared. Add 5x, and then can bring our 6 over. We can subtract 6. Divide both sides by 10 and simplify, and you get x equals -1/5. So here I'll give a moment to take a look at this solution here, but that would be a number that solves both of these things. And now I'm just realizing one thing I said you should do first so that you don't forget, state your restrictions. So in this case, x could not equal 4. And x could not equal -2. Unlike logarithms, this is a does not equal sign. It doesn't have to be greater than or less than. It just can't be equal to those numbers because you can't divide by 0. Do the restrictions first so that you don't forget come the end, like I almost did, to check. But in this case, no extraneous solutions. So this one, I didn't like how I initially wrote it. I actually did it 2 separate times. Just a few different ways you could think about it. And I kind of went back and thought that maybe this might make more sense. So because I had explained, so yes, we need to state our restrictions. So x cannot be equal to 0 here. And I had talked about you kind of want to multiply out your denominators. Now, you can think of it individually. You can think of it, I got to multiply by 3x. I got to multiply by 4. And, well, we already multiplied by an x here, so that's actually already going to help us get rid of the x's if we multiply everything out there. So you could think of it in two ways. You could think of it, well, if you multiply by 3x and you multiply by 4, you're multiplying by 12x. Or if you think of it like the lowest common denominator would be 12x. They all have at least a factor of 3, a factor of 4, and a factor of x. Then you either want to think of it as putting an entire fraction over 12x, which is kind of where I was starting here. I know I crossed it out, but you could think about it that way. I'm suggesting that maybe if that's the lowest common denominator or like the lowest common multiple of those three things, that's what you want to multiply by here. And that's going to guarantee that we can cancel something from everything here. So for instance, our x and our x cancel out. Oh, it didn't really show up. And then 12 and 3, we get left with a 4. 12 and 4, we get left with a 3. The x doesn't cancel in that one. Oh, is it going to focus? The very last one, I have an x and an x. And the 12 doesn't cancel in that last one. So I'm going to take a moment here and write out what do we have left. Okay, so what do we get left with? Well, we have 4 times 5. We had 3x times 5. And we had 3 times 12. So we can say well, that's 20 plus 15x equals 36. Move the 20 over, 15x equals 16, and eventually you get x equals 16 over 15 as your final answer. Not obvious from looking at this equation. Oh, 16, 15 is going to be the answer, but from solving it, that is the answer we get. That's the only x value that would work in that equation. So this next one, we just finished this one here. I did write it out. It's not maybe immediately obvious what is our lowest common denominator, but on this very left fraction, it might help if we factor out n squared, and we get n squared times n plus 5. And so that really, that is the term that we are trying to match here. Now, we could do it the exact same way that I did here, and that was like multiplying by the lowest common denominator, and that's going to guarantee it's going to get rid of all those denominators. That would definitely work in this case with a lowest common denominator of n squared times n plus 5. Now I'm going to show the alternate way as well, because I think some people will find this method easier. Some people will find it easier to think about it from fractions. And so let's take a look at that method here. So using this kind of alternate method, well, the first thing, I wrote down restrictions with this factored form. N can't be 0, n can't be -5. They don't work in the rational form. And then trying to match this denominator. So here we have n plus 5. We're missing a multiplication by n squared. So I multiplied the top and the bottom of this fraction by n squared. And vice versa, this one was missing an n plus 5. So I multiplied the top and the bottom by n plus 5. This one already had everything it needed. And so we get this here with the same denominator every single time. So we can combine the two on the right. And now I have a numerator over a denominator and a different numerator over the same denominator, and they have to be equal. Well, that can only be true if this top equals this top, because the bottoms are already the same. So this top could equal the other top, and then we just have a quadratic to solve. So subtract 5 from both sides, factor and we get 0 and -1/4, but 0 is extraneous because it was one of our restrictions. We couldn't have n be 0 over here, or really in this one either, and n can't be 0 from here. So that's a look at that full solution. I'm going to hold it here just for a moment in case you're trying to pause and take a look. But this is a look at a slightly different way of thinking, where you could think of it as all fractions and then wait till you have a common denominator and get rid of it. Now this is going to be a slightly slower method than straight up canceling right off the bat. So you do what feels right, but this way is going to be slightly quicker if you come to terms with it. Got one more on this sheet, so let's take a look. Well, at least this page. I guess we have some on the back here, but let's take a look at this one right here. So yes, we have restrictions of 0 and +1, because 1 minus 1 would be 0. And, well, there's no way to multiply either one of those to get the other thing, the other denominator. So our lowest common denominator should include both those terms. And so I did kind of what I did the first time over here, multiplied by the number that was our lowest common denominator. And so if this is our lowest common denominator, multiplied that 1 by x times 1 minus x, that 2 by x times 1 minus x. Here, this is just a single term, but I still got to multiply it by x times 1 minus x, and then 1 times x times 1 minus x. And so because I've multiplied every term by the same thing, then both sides are still equal. And so let's see what cancels here. Okay, so the x is canceled out in these first two terms. This one, nothing canceled out because there's no fraction. 1 minus x is canceled out. So we can write 1 minus x equals 2 times 1 minus x plus x times 1 minus x plus x. Expand out the brackets. I moved everything to the left here because that's going to help make that x squared be a positive. And then we get something that does not factor. So we can use our good old friend quadratic formula, and that's going to help solve this one, which none of these answers are going to be equal to either of our restrictions. So both those answers should be legit. Again, very hard to predict that's the right number here for x. So you don't want to, you never want to do the guess and check, but you definitely don't want to do guess and check here. A lot of the times these are some strange or looking numbers. 16 over 15, something with a plus or minus square root. You want to know how to do this algebraically. And last but not least, I think, yes, there's nothing on the back here. Example 2, a word problem. Salt water is floating into a large tank that contains pure water. The concentration of the salt, C, in the tank at t minutes is given by this equation here. Oh, look, a rational equation, a rational function, where C is measured in grams per liter. Okay, they give us units. They even write grams per liter down in this part. We want to know, when does the salt concentration in the tank reach 3.75 grams per liter? So if we are looking for the salt concentration, that's our C of t. And so right away we can sub that into our equation for C of t. We want to know, when is that 3.75? And we know t cannot equal -25 from this equation. That's fine. T is time. Time probably, well, sometimes it can't be negative. It doesn't make sense for the problem. It doesn't really tell us when the time's starting to be counted here. But either way, multiply your denominator out. We can expand those brackets. And then I moved the t's to one side, the non-t's to the other, and divided by 6.25, and I get t equals 15. So I could say, well, therefore the tank reaches that salt concentration after 15 minutes, because this t was measured in minutes. So I'll zoom out and just kind of let you take a look at that one. And we got one more question here. So this one here, yeah, what's the concentration in that tank after a long time? Well, in math, when we talk about a long time, think of like when t is really big. So when the t in this equation up here is really big, what is happening? And for a rational equation, when we talk about like what happens as our independent variables getting really big, positive, or really small, like a really big negative, think t approaches infinity, which is really like your horizontal asymptote. So that's what's happening as that t gets really big. It's going to approach that horizontal asymptote. And so if I look back at my function here, I have a t to the power of 1, a t to the power of 1. So they are the same degree. So I can just look at the leading coefficients, 10 over 1. My horizontal asymptote's at 10. So the concentration after a long time will be 10 grams per liter.